Welcome back, students. In this video, I want to talk about solvent choice for our acid-base reactions. When you get into organic chemistry, you've taken general chemistry, you've been in general chemistry lab, and you're really used to water being your solvent. But when you're in organic chemistry, a lot of times water isn't going to work. And I want to show you why that is. So here I have a reaction that's drawn where I have a base and also an acid. And let's pretend that water is our solvent. And we need solvents because solvents will take solid compounds and solubilize them so that they can react with other things. Now, this particular example, if you actually look it up, that acid is technically a gas, but let's pretend it's a liquid. What would happen if these three things were in the reaction mixture at once is not what we want to have happen. Let me draw what we want to have happen with green arrows. What we want to have happen is our nitrogen to attack this hydrogen, pull off that proton, and have the electrons go on to the carbon triple bond. But what would actually happen is you would have your nitrogen attack the hydrogen of water. And why is that? Why would we end up pulling off one of our water's protons instead of the proton that we want? And it's all about acid strength. Water is a stronger acid than the proton that's on the carbon that's in the triple bond. And you can't stop the base from attacking the stronger acid. It's going to do that. So what will actually happen is what I'm going to draw in blue arrows is your base would attack this proton because water is a stronger acid, and you would end up with NH3 at the end, right, which is ammonia. This part wouldn't change, and then hydroxide ion. So congratulations, you just made hydroxide. You could have just bought sodium hydroxide if you really needed hydroxide that badly. Therefore, we cannot use water as our solvent in this reaction. If water is unavailable, what are we going to use? Here's a list of some common organic solvents. Some of them I drew out the structure. Like here, I've drawn out the structure for hexane, the structure for tetrahydrofuran, which is THF, the structure for dichloromethane, which sometimes we abbreviate as DCM, and the structure for diethyl ether, which is what we just call ether. Carbon tetrachloride isn't used as commonly anymore because it is a carcinogen, and sometimes you'll see people call it carbon tet instead of carbon tetrachloride. These three we'll see just as abbreviations because that's just common in organic chemistry. So what we'll tend to do is use an organic solvent that isn't reactive in our acid-base reaction if we end up needing a solvent at all. Remember how we said in REO that we looked at atom, resonance, induction, and orbital. But you know what? Solvent can play a role too. And when we look at solvents, your pKa of an acid can actually be affected by how well that solvent stabilizes the conjugate base. So I have two ideas here about solvents. For the first idea, it is that a conjugate base that's large and bulky, like this one, which is called tert butoxide, the solvent can't surround it very well, because you have so much bulk over here from all of those carbon groups. And remember that it's a carbon and then there's hydrogens attached, so really it is taking up quite a bit of space. So if I just try to imagine how much space this is taking up, what will occur then is if I have a solvent molecule, maybe only one or two solvent molecules, maybe three, can really fit around that negative oxygen. Whereas if I have something that's less bulky, so this part has a less bulky carbon branch, then I can have 1, 2, 3, maybe 4 solvent molecules surrounding that oxygen. And if your solvent is polar, if your oxygen is negative, then the partial positive side of your solvent will line up with the negative. And then over on the other side of the solvent molecule will be where your partial negative is. What's happening is your negatively charged conjugate bases are able to then donate some electron density to the positive end of your polar solvents. And remember that if we're donating electron density, that's a stabilizing effect. The more small donations you can have by having more solvent molecules surround your conjugate base, the more stable that conjugate base is going to be. This means that your smaller bases, so smaller bases, are more readily stabilized by solvent. If we kind of fold this back into the idea of ARIO, if we look at these two conjugate bases and we're trying to decide which one is going to be the more stable conjugate base, ARIO doesn't do anything for us. They got the same atom, they got the same resonance, they don't have induction, they have the same orbital. It doesn't do us any good. So what will help us is recognizing that the bulkier the base, the harder it is for the solvent molecules to surround that and help stabilize it. Another idea with salivating effects is the idea that the more polar the solvent, the better it can stabilize the conjugate base. So if you have a molecule that's a solvent molecule that's quite polar, it's able to stabilize a conjugate base better than a medium or non-polar solvent molecule. One other thing I want to point out in this chapter is the counter ions that you may see when we're drawing bases. When you were in general chemistry, you saw spectator ions, and those spectator ions were just there to get the ion that you cared about into the reaction. And we're going to see those pop up again in organic chemistry. We're going to see two different ways of writing bases. So here is one of my favorite bases, sodium amide. When we see sodium amide written, it can be written as NaNH2, where what you need to do is recognize that the Na is just hanging out positive sodium ion, and the NH2 is the base that we care about. Sometimes in organic chemistry, we will also write just NH2 minus, because that makes it easier for you, the student, to recognize that this is a base because it has electrons and it has a negative charge and it's going to abstract a proton. But when you get used to this way, then when we transition or accidentally write NaNH2, you don't know what it is anymore. So you just kind of have to be mentally aware. Don't freak out if you end up seeing slight variations in how we write these things, because as the teacher, the problem is that the teacher's seen this so often that we forget that to a brand new student, these are very different for you, because in actuality, they are the same. They're just a different notation. So the one on the left is showing the counter ion, the spectator ion of sodium. The one on the right is saying, you know what, we don't care about that sodium ion. It doesn't do anything in the reaction, so we're just going to focus on the actual base and how the base looks. Let's wrap up. In this video, we talked about choosing solvents, where a lot of times water is not going to be a good choice, because if water is more acidic than the acid that you're trying to react with, then you're not going to get what you want at the end of your reaction. We also talked about how solvents can create a stronger base because it is stabilizing that conjugate base by surrounding the conjugate base with solvent molecules. Those are called salivating effects. We gave you a list of some common organic solvents and then just gave you a quick reminder about spectator ions. As always, thanks for your attention. This is Katoni signing out.